A very good morning. We thank you all for your constant engagement and encouragement. We welcome you to the 28th episode of Gyaniki Tech Talk. Shortages of semiconductors are battering automakers and tech giants, raising alarms from Washington to Brussels to Beijing. Not just that, lack of semiconductor manufacturing is turning out to be the biggest hurdle in India's trust with self-reliance in electronics. It requires out-of-the-box thinking by the government and the industry to overcome all these issues it's facing. To discuss on these issues, I would like to welcome today's guest, Mr. Narayan Prasad, who is who is a semiconductor professional with 20 years of experience in chip and system design. He has developed cutting-edge chips for Cisco, Samsung, Microsoft, Apple, but he's also worked with Texas Instruments, Broadcom, Intel, ARM. He co-founded the AMP, Advanced Monolithic Power Semiconductors, and currently serves as a technical consultant to other startups including HQ and Pi Semiconductors. Besides chip design, he is deeply drawn towards automotive electronic systems, specifically autonomous and connected cars. Making use of his spare time, he learns and cultivates technological developments on this front. We welcome you, sir, on behalf of Team Gyaniki and today's audience.
Yeah, thanks, Varshini. So I will start this talk and let me share my slide deck. The idea is to, in today's talk, to go over how this semiconductor industry operates, uh, how is the supply chain end-to-end organized, and in the specific context of the automotive industry, what are the things that have happened in the past? Where are we today in terms of the shortages? We try to understand what are the some of the events which have triggered it, and then what is the opportunity and challenges for the future for the global ecosystem, as well as specifically where can India play a bigger role in the future. So with that, let me start the presentation. So everybody has what they call a dream home, right? How you want to your house has to come up through. You would have envisioned it that it should have this much frontage, these many floors, these many features, these many rooms, and I would do the decoration this way. And when you want to realize your dream home, you don't go straight away, start buying the materials, the bricks, the furniture, and start putting to it. The first thing you will try to do is to build up a mock-up or a virtualization of it. Essentially what we need is a blueprint. How this is going to shape up, including the exact dimensions of it, where are going to be the doors, the exits, the windows. You can have a floor by floor markup, and you can even have a virtual walkthrough to that house that you're going to finally live in and enjoy. You can do, I'm going in the extreme here. You could have a virtual reality monitor where you walk through and see room by room how it will turn up in different light conditions, in different environments. How does it look at day, at the night, and all those things. And once you are convinced that, okay,
Narayan, just 1 second. I think we are not seeing the full screen. We are still seeing the first page of the PPT.
yeah. Oh, okay. I'm in the second slide, Shekhar.
Yes.
Are you seeing?
No, we
No?
are not seeing that. So if you can go to full
Let me
screen
do
mode.
this.
Yeah.
Let me do it again. How about now, Shekhar?
Yes, this is perfect.
Okay. So what I was telling is basically you would start with a blueprint, have all the details nailed down, and then go into the actual physical transformation into the actual house that you want to build finally. Silicon chips, semiconductor chips are also done in a very similar fashion. Before you can realize it into a physical form, you build a mock-up of it. You're able to put a different set of building blocks elements. Some are available off the shelf, like your furniture fixtures. Some you will have to custom make it. And once you put all these different elements together to comprise a chip, you can actually, like how you did a virtual walkthrough, you will be able to simulate how this chip will work in the final environment. All this is done with software tools and software models of the final realization. And once you have a blueprint of that silicon, that is the end of the design phase of it. And at that phase is where you will move to manufacturing. So the semiconductor chip itself, broadly, it's in two phases, a design phase and a manufacturing phase. And when you build silicon, I mean, when you build a house, you're not building one house. You're actually building an entire city, an entire metropolis. So, how a metropolis will have their commercial areas, industrial areas, people, areas for people to reside, public areas, sports arenas, entertainment zones, and how do you connect them? You need the roads, you need the metros, you need the suburban trains. And if this metropolis has to talk to another metropolis, if you want to travel, then you need your rail and road links, the airports, or your shipping. Everything comes together in a metropolis. The same way, a silicon is also a metropolis in that so many different functions. For example, this is what we call as a micro photograph of an Intel processor. You can see some very repeated structures. This is what you call as the core or the central processing cores of the chip. This has all the elements like in a big metropolis. You have some of the communication interfaces which go and talk to off chip or other components in your board. Then you have memory. Then you have some of the elements which does the signal processing aspect for you. And then there are also various monitors and power regulators that make the chip operate in a very reliable condition across temperature and other environmental conditions. So, this silicon metropolis, at the heart of it is a transistor, like how people are at the hearts of a metropolis. A transistor is the heart of a silicon chip. So, again, each individual or each person in a city has his own characteristics, his own interest, his own skills, his own employment, and you need various different people to operate a city. There are the engineers, the doctors, the 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 medical staff, the government staff. They all work together to make the metropolis move and build over time, operate in a very efficient manner. In the same way, though the building block of your silicon chip is a transistor, the transistor itself is abstracted to perform different functions, like the characteristics of a person or a set of people. There are certain transistors which behave as off or on elements. You would have heard of the logic state 0 and 1. So, when you are able to manipulate transistors in that way, you are able to do certain functions, and that is at the heart of the digital processing. You can have certain transistors configured to hold information, again, a logic 0 or a logic 1, and they will serve as the memory elements for the chip. Then you need some analog to interface to the real world. For example, if you're talking on a phone, you need a microphone which translates your voice into an electric signal that the chip can understand and process. You take a picture through your camera phone, that is also an image. The image has to be converted into a database that can be stored in the memory and recalled or sent forward to anybody in your network. So those are the analog elements that help this chip to communicate to the real. There are also RF, radio frequency, uh, transistors which are optimized to work at gigahertz range. So it could be from 2 to 60 or 100 gigahertz. And these serve functions for your chip in the manner that, let's say, you have your Wi-Fi connectivity, your 4G, 5G networks, Bluetooth, GPS, um, even your face recognition as something like a radar, which bounces back from your profile and the camera processes it. So those are the RF elements in a silicon chip. There are also power transistors who ensure that the chip always operates in a very optimum power, voltage, current, and temperature level. So they kind of buffer the environmental changes. You could have line voltage changes, but these should not ripple down and affect the performance of the chip. So they do the regulation function. So power management, power regulation, how do we always operate at the best efficiency in terms of, let's say, to save power, be more environmental conscious, or to save the battery life because it's a mobile or a handheld device, that falls in the realm of the power transistors. And then there are very, very specialized MEMS microelectromechanical structures which are basically some of the, for example, the phone or the speaker as a diaphragm, which when the sound wave impinges, it moves and creates the electric signal. Even those structures at a very miniaturized level can be imprinted on silicon wafers. We will see how that process is done and be able to realize these functions. The classic example for the automotive industry, you would have heard of accelerometers and gyroscopes, very commonly used for your crash bag, airbag deployments, and even more today for the autonomous vehicles, they serve to help update the GPS. So that's a very good example of MEMS systems and transistors. So any single silicon chip will have these ingredients, maybe not all, but they all come together to realize a certain usable function. And what is that usable function will depend on the market or the end case in which these will go and be utilized. So you have the vast consumer markets, your desktops, laptops, tablets, smartphones, wearables, whatever it is, they all fall in the consumer market. Communications and enterprise, your servers, data centers, which help you to communicate across the globe, send data, voice. Automotive, we will look at that more in detail in this talk. Industrial, of course, military, defense, and medical. They're broadly the end segments in which these chips are extensively used. So, what does it take to actually make a chip? So, to make a chip, like how we said, how you construct a house, you would have to do it in two phases, a design phase and a manufacturing phase. A design phase starts with an idea. Okay, I need to build this chip for, let's say, an autonomous navigation radar system. So that is the problem to solve, or that's the idea that I have a unique idea, probably patented, or I know how to realize it and make it better in terms of the specifications. So that's the idea you start with. And when you want to do the design, you need a set of expertise of people with different backgrounds, like how you need to construct a house. You need the electrician, the civil engineer, the architect, the plumber, carpenter. All of them come together to realize that house for you. To realize the design also today, it is highly specialized and you need people with various expertise. So, along with the idea and the expertise, you need the simulation software, which can tell you that when you put these building blocks together and you give a certain stimuli, this is how it will respond. Because this cannot be a paper and pen effort anymore. So, the tool can take in your inputs, do a simulation for you, come up with a pass fail or report that it's not working as per what you've designed, go back and fix it. So that's an iterative process. It is the verification which is extensively done to ensure that all the building blocks come together in an intelligent and meaningful way and is able to do the intended function. In this case, the radar signal processing. I'm just giving you an example here. So out of these three, the idea, the set of people with expertise, and the EDA software, you come with what is the chip blueprint. It is it is like essentially saying that if you have these transistor building blocks and you connect them and build this, put them together in this way, you are realizing the intended function. So it's basically, you can think of it as a software database. And that is pretty much where our design phase ends and where things can get even more interesting in today's context. The chip blueprint or the software database has to go to the foundry or what is the fabrication plant, or in a very short form, what is called the fab. The fab is like the malls of the metropolis, the most happening place today. And the foundry itself, if you this snapshot or the picture here does not do justice to what the actual foundry is. It is an enormous machinery, set of machinery, highly specialized, where this blueprint is taken and it is realized into a silicon chip. To realize that, the starting point is what we call as a raw wafer. It is nothing more than, let's say, taking sand, purifying it, melting it, like how you made uh, pretty much the same way like how you make glass, but it's a very, very highly refined process. You can have impurities or defects to the parts per billion kind of a thing. When you purify it to that extent, you will convert them into these kind of cylindrical rods. And from this rod, this is a silicon ingot, what they call, you will slice it to get what are called the wafers, the discs that you see here. There are various standard dimensions for it. The largest one is like your 12-inch pizza. These are called the 300 wafers. And it is, when you look at the raw wafer, it is like a highly polished mirror. And that is your starting point for taking this blueprint and imprinting into it. And to do the imprint, you need a lot of specialized chemicals. A classic example, some I don't know how many people can relate here, is the film photography. I mean, today it's all digital cameras, but back in these days, you would get a film roll and you would expose to light through a shutter on the camera. So the light will go and imprint on the film to create the image replica. You will take this image to a processing lab. There they will develop with chemicals and then realize, invert it again to the actual colors that you want, and then print it on whatever the cards that you want. That's olden, but this is exactly what is being done in a foundry using the silicon wafers and specialty chemicals, but at a very, 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 very minute or miniature levels. We are talking micrometers and tens of nanometers today. So that's kind of resolution, precision, or um, um, yeah, the depth to which these kind of rendering of the blueprint happens. The foundry itself, to be able to blueprint this onto the silicon wafer, you need several steps: something to develop, something to deposit, coat, etch, and you keep doing this over and over multiple times, that you will build this slowly, layer by layer. It's like building a cake that you want. You have a sponge, a cream, a certain filling, then one more sponge, then whatever you want to top with, finally the cherry. So almost like how you build a cake bottom up, the silicon wafer is grown to imprint the blueprint onto that substrate. There's a lot of machinery. The industry for the foundry itself, it is called semiconductor manufacturing equipment, and each of which there are very, very specialized expertise for each of these equipment, which is a domain by itself. You need some of the plasma treatment, some of the deposition for the diffusion, some of them are very specialized inspection and etching. All of that is what all these different equipment is what comes together in this foundry. And when you go through this processing steps, which is typically handled by a set of robos, usually they run on the top, and there is usually like a track around. So they will run on the top, and then whenever a machine is needed to be loaded or unloaded, it will drop down these pillars, operate it, and then take it to the next one. It has a very sophisticated and a highly automated system. So you will have foundries or fabs which can be operated with just about 20 people. But those 20 people are very highly uh, technical and skilled workers, um, to be able to root cause when things go wrong and correct for it. So that's how a foundry comes. You will have heard of the foundry issues today, the bottlenecks which we see. We will look at it also later why it has come to that point. Out of this processing steps, which is typically there are about 40 to 50 masks or steps in the fabrication process. It typically takes about a day or a day and a half. So we're looking at about 2 to 3 months from when you get the blueprint to when you finally realize what is this finished wafer or processed wafer. So that's kind of the lead time. And the typical design time, right from a concept idea to when you can come up with a blueprint, depending on the complexity, can be again 6 months to easily a year. So these are roughly the time frames that we have. And this finished wafer by itself does not serve the intended function. One, it is super thin. So, like your actual chip, potato chip, it can just easily crack on a very small stress. So, you need something to give it the mechanical stability. That happens when we do the packaging. And these packaging houses, they go by the term called OSAT, outsourced assembly and test. So whatever needed to package it, assemble it, and then test it is taken away from the foundry, because this is again its own specialized function. The foundry would like to focus on the key manufacturing aspect of getting the fabricated wafers. So the OSAT, when you package it finally, You realize it in a form where one, it has the mechanical strength. Two, it has the necessary protective molding so that it is not affected by environmental conditions. And three is you have brought out what are these called as pins. These are the electrical connections which you can send data into a chip. And also there are outputs through which you get processed information out. So these are the channels through which you can talk to the chip and get back data. And multiple such chips come together in your PCB, like in your smartphone, as an example, or a motherboard of an Intel gaming desktop. Multiple chips with multiple different functions, they all end up on a common substrate, which is a PCB. And that PCB is enclosed in another medium to finally realize the intended devices that we want, including a high-end gaming desktop or your regular smartphones that you see extensively today. So this, in a way, is an end-to-end. I've really condensed it. I mean, you can keep going down and uh, it's like an onion, keep peeling layers, and you will see there is complexity in the software part of it. There are very specialized people whose job is to develop wafers and keep the supply chain running. The very good chemical companies, BASF, Merck, etc., who only come and deliver these chemicals for the etching and deposition. And then, like I said, packaging assembly houses, whose job is only to do the packaging of the chips. So, as I said, this is a 6 months to a year's effort easily. The foundry stage would approximately take 2 to 3 months. It takes another couple of weeks, depending on the chip's complexity, in the sense of how many interface pins are there, what kind of pitch, what kind of package. See, another 2 to 3 weeks. So if you had an idea today, right, I would say it's going to take you about 15 to 18 months to finally see this realizable form in hand, a physical realizable chip in your hand. That's the timelines and the complexity of how the industry is organized today. And multiple vendors focus on the different aspects to deliver the most efficient in terms of cost control and the performance also. So, like I said, there are two phases, right? The design and the manufacturing. The foundries that we mentioned today purely focus on the manufacturing aspects to realize the physical form. And companies which are focused on the design, they go by the more common terminology called fabless. They don't have any captive foundry or manufacturing unit to go produce this chip. They will have to rely on the foundry to do it for them. So some kind of service agreements need to be entered between these fabless companies. We'll see a few examples. And the foundry, again, we'll see some of the examples. Today, I think the key players, many of them you will be very familiar with. TSMC, which own up to 50% of the foundry market, and then the other players capturing about 25 to 30% between them. SMIC, based out of China, TSMC out of Taiwan, UMC is also based in Taiwan, and GF is that one foundry which has a footprint in Europe, the US, and Asia. There is another class by which there are still some companies who do both their own design as well as control their manufacturing process. They go by the term, the short form called IDM. integrated device manufacturers. Intel is a very good example of that. The processors they do are designed and manufactured at their own facilities. There are other vendors, some of them you would be familiar with, Samsung, Micron, SK Hynix. They play a large part on the memory side. So if somebody needs a DRAM, a dynamic random access memory chip, or a flash memory for tons of storage, these are the guys who design and manufacture it end to end. What is also, I mean, this partition between a fabless and a foundry, this has happened in the last, I would say, about 20 to 25 years. Earlier, a company like TI used to have its own foundry and used to design and manufacture it at its own facility. It was an idea, but over time, they saw that handling both was increasing the complexity, and they saw more value in doing the design and leave the manufacturing aspects to others. So, what these set of players did, what they are called as Fab Light, is that they still have some legacy or old manufacturing facility because some of the products still are good enough to be manufactured in those technologies. But for the newer ones, we go to these foundry. So they are operating on the Fab Light model. And the fabless guys, there are lots and lots of companies, startups. I have not captured them, but some of the names that you can quickly relate to, the Broadcoms and the Qualcomms on the communication side, NVIDIA for the graphics, AMD for the competition with Intel and their own processors for the desktop and enterprise. Some of the software companies also today are hardware and chip design houses, including the Microsofts, the Googles, Apple, and Facebook. And of course, on the automotive side, we know Bosch is designing, and in fact, it has today its own foundry also out of Dresden. So, and Tesla has been very active in driving their own chips and integrating systems on their end. So, this is like how the semiconductor universe, in terms of the specialization and industry key players, how they are organized into these four buckets. Overly simplified here, but you get a picture of how the whole thing comes together between design and manufacturing. And like I showed, the fabless, the foundry, the IDMs, and the fablite companies, all these guys, when they go and make a chip, for example, AMD has to do their what they're called as epic processors. They not need to go and talk to TSMC first, saying that, hey, I'm going to design this chip. It is, we want to set it to market in about 2 years time. TSMC will say that, okay, if you want it in 2023 or 2024, you would have to give us the blueprint by a year in advance so that we can have the initial samples built for you, ensure it works to your specifications. And once you're convinced this looks good, I can go build the volumes that you want for you. If there are 100 million laptops, I will need 100 million CPUs to go along with it. So they need to, one, agree on the timelines, two, on the capacity, three is what I call as the process technology node. What happens there is not all silicon functions are realized in the same way. What we said as the pitch or the geometries or how small a transistor is, because the smaller the transistor, the more number of transistors can you pack in the same area. That means you can realize more and more integrated functions, which means it is cheaper per unit area or cheaper per function to go to smaller and smaller geometries. So when I say geometry, traditionally in the past, it was referred to as the space between, or what is called as the transistor's gate length. Uh, it is the channel which allows the current to flow between one terminal to the other. And when this gate is turned off, the channel is cut off. That channel used to be in the past be referred as 45 nanometer, 28 nanometer, 22 nanometer. At some point in time, we changed fundamentally how these transistors were made. So those pitches did not make sense. But every reduction means that you are reducing the area by half. So today's leading edge geometries, whatever you say, 10 nanometer, 7 nanometer, 5 nanometer, that means progressively in each of these generations, the area is reduced by a factor of 2 or about 1.7 or 1.8 as per the data that is given by TSMC. That is your Moore's law by which the semiconductor industry has been operating for a long time. That transistor densities double almost every 18 months. And 18 months is kind of what it takes to also move from one design to the other. That's, I mean, we can go and discuss Moore's law in an entire discussion separately. But that cadence is what has pushed the industry to go keep innovating, packing more features, packing more transistors on the same silicon. The silicon wafer has not fundamentally changed, but you are able to etch finer and finer geometries, place more and more transistors, and realize more and more sophisticated functions that you're able to pack something like a Samsung or a Qualcomm processor on such a smartphone, such a small smartphone, right? That's the power of Moore's law. So, this, I mean, leading up to this point, we've just analyzed how the semiconductor operates, come into design and manufacturing phases. What is a typical timeline to go from design to the final realizable product? What I want to introduce here is very specific to the different end users. Where is the automotive semiconductor market? So these two pie charts essentially say, if you take the one on the left, it tells you who are the key players today for the semiconductor chips. The semiconductor chips themselves, when they develop, they go into these systems companies, into the tier one suppliers who build the modules, and these modules are then delivered to the OEMs, which are the car manufacturers, who integrate these electronic functions with the rest of the car systems to finally realize the vehicle of choice. So, if you see the market today, the NXP and Infineon, between them probably there is only a 1% difference. Though they are the leaders of the pack, they still account for only one fourth of the market. The market by itself is heavily splintered into so many players. 40% is the rest of the industry by revenue. The second thing is what I wanted to highlight with the pie chart on the right is that what are the different chips that go into automotive today? The future is, of course, up for discussion. Today, it's a lot of control processor units, application specific ICs, a lot of discrete sensors, and the MCUs, the microcontroller units that together occupy close to 50% of the semiconductor footprint in a car, which is you can relate to the car with the different kind of sensors, body sensors, window sensors, rain sensors, light sensors, humidity, pressure. will all need the individual sensing actuation chips and the microcontroller and the processing unit to go along with it. So that's why today I read somewhere that for a Volkswagen car, there are as many as 100 to 120 different control units to pick and integrate into a car. I mean, not all 100 will go through, but that's the superset in which they start with and go customize it to each vehicle's requirements. And between them, that accounts for roughly $400 worth of semiconductor chips. That's a data point for us to digest here. And when you see the typical revenue percentage across different segments here, what we have is at least 5 different segments, including auto and industrial. Over the last 20-25 years, if you see the trajectory, automotive has definitely grown, but they still today are only 10% by market revenue. Semiconductor chips today, we are telling is about $400 billion. It is going to increase by another 25% this year. It's going to reach 500 billion. But then the slice of that pie that automotive industry today takes is only about 40 billion or even 30 billion today. So it is still not a big player when it comes to semiconductor chips. That's one market realization that we have today. Second is these chips that we want in the car, they are manufactured in mature processes. That is, when I said the gate pitch and we said 28 nanometer, 45 nanometer, these go back to the older or processes which have been in the play last 10 years, 12 years. It is preferred because these have been already tested, all have been, the processes have been fine tuned. Any defects, anything that is unforeseen is already fixed in the system, very stable, so that we don't have to worry about any failures. This all goes as part of the functional safety requirements and standards also. But when you make it in a mature process, that means that there is a very little scope to eke out money out of them for the foundries. They've already done it. They've already moved to the more interesting challenges up the road where they see that if they solve it and they're able to uh, deliver more functionality in the same unit area, I get more returns on my investment. So for them, the focus is on the consumer and communications part because that gives them better and better returns. This is still okay because whatever is being manufactured in the mature process, cars with a lifetime of 10 years or more in play, they get a steady stream over their lifetime. So it is steady, but not significant for the foundries. Like I said, the functional safety reliability are very, very stringent. There is the AEC-Q 100, 101 specifications, the ISO 26262. So all of them, not just for hardware, even for software, enforce a lot of redundancy, and it increases the barrier for new players to come into the automotive industry. As I showed in the first pie chart here, among the various players or for the semiconductor chips, they are highly fragmented, and but once you are in the market, you have to sustain them for a very, very long time. The 10-year life cycles of the car, and up to 15 years, you would have to keep the volumes in play. That is also one reason why the players, right, either TI, NXP, Infineon, or ST, they are in the fab light model. They have not gone fabless because the fabs that they own, they can continue to churn these automotive semiconductor chips for them, and we don't have to scrap those machinery out. So that's a play that these companies have done to stay fab light. And the last one is, as I said, the margins were very slim, not very significant, because if I want a microcontroller, I will, for 100% volume, I will not give all the 100% to a single customer like Infineon. So I will carve it up saying 60% I will source it from Infineon, 40 from TI. Or I could have three-way vendor agreements also between NXP, ST, and TI. I could do a 40-30-30 split. So when you do that way, it kind of reduces your dependency on a single semiconductor vendor. It reduces the risk that tomorrow, if they go out of business or see a supply constraint, then you have the other two guys to pick up for you. So these are some of the at least five key things in the automotive semiconductors. These are what is business as usual today for those chips that are manufactured out. On the OEMs, on the car manufacturers, they've always operated on a just-in-time philosophy that I need a million chips in February. Okay, I will go back to my supplier and ask him to start it because there are about 3 to 4 months lead time. I will go just that much earlier and ask him to start ramping up so that I get those million parts in February. So this, because being inventory light, frees up capital, gives them the flexibility to go pivot to a new requirement easily today. But that is also one of the reasons, keep in mind, that this constraint has come about, the just in time. Which leads us now, given how business has been done for the semiconductor chips in the automotive sector, what has happened in the last year and a half in terms of this supply shortage? So, right around the end of 2019, we had the official news coming out of China for the COVID. And then over the next quarter, we had the virus spread over parts of Asia, Europe, and North America. So, and when it started proliferating extensively, cities, states, countries went into lockdowns, and some of the manufacturing facilities, including car assembly, they went into global shutdowns. And mobility was highly curtailed across geographies. Need to be a very, very valid reason to move around. So when the industry saw that, that we were going into a reduced demand, a quarter later or around in the June timeframe, they went ahead and cut the orders for their electronic components. And so it rippled through their tier one suppliers into the semiconductor vendors who were providing for it that we don't need these orders looking up. So that was the first reaction, or the reaction to the aftermath of the COVID spread. But then something interesting happened that towards the end of the year, after the first wave, and with the possibility of vaccinations in the horizon, there was a recovery for demand of personal vehicles. People wanted to move. They had been locked up for over a year, but then public transportation was not available. They saw the personal vehicles as a means to go move around. They had money locked up over again a year. You didn't spend on it, neither the New Year, nor the Diwali, or nor the holiday season. People opened their wallets the year before, suddenly were sitting on a lot of money, and they wanted to move around, and they saw that the personal vehicle was the best way to give them that safety cocoon and still go out. So these people started going and getting personal vehicles, the demand went up. But then what happened in the June timeframe when the components orders were reduced started biting the manufacturers in the early Q1 of this year. Um, so there's a kind of a very bad situation to be in where the demands were going up, but then we were running short of the supplies. So everybody in the world, Ford, GM, the Mahindras, Tatas, even BMW, Volkswagen, many people were affected. We kept hearing this news for at least a quarter, even now today, because it is not something that will go away in the short term. A few have buffered through this. They have planned their inventory better. Tesla is one. They still have shortages. Toyota is another. They have planned. They don't um, depend on the just-in-time. Though we give Japanese the credit for doing the just-in-time methodology, they are now on the other side of the fence where they have the necessary parts stockpiled for at least 1 quarter. So they're able to, or at least they weather the storm better than the other manufacturers. But this is not just COVID alone. You don't have to, though COVID triggered this, you don't have to say that COVID alone was responsible for what has happened in the last year or year and a half. Certain industry practices, like what we have seen in the previous slide, whatever you called as business as usual, and some of the supply chain practices of just in time inventory management, all of them together has created this scenario. And like Murphy's Law, when things, if you think things will go wrong, it will. There were more such incidents over the last quarter again, where the Texas winter storm affected power supply, because of which certain foundry or manufacturing facilities had a downtime. Both NXP and Infineon have big foundries in Austin, which was affected to over a month or two, and that also curtailed the already short production. Second was the Renesas had a fire in their Japan facility in the month of March, which again forced them to shut down. It is just recovering and coming back to full production as we speak today. And then the Suez Canal getting stuck, the Evergreen ship getting stuck, and blockading the movements of equipment for at least a week. That is going to create a backlog which will ripple to more than a month. These have also added what you call as fuel to fire and made the already stretched supply chain to be even more constrained. So this all together is like what you call a perfect storm. Past practices, the COVID scenario, and certain very one-off incidences which have amplified because of the existing conditions, all of them creating the shortage and um, and throwing the supply chain in disruption. So, as with um, any such crisis, the industry will, of course, recover. People will go back in the short term to justify with whatever supplies they get what are the vehicles that we want to deliver that will fetch you um, the price. For example, Tesla wants to focus on its Model 3 and Model X, the Model S and Model Y, which are premium. They don't have uh, a big enough market. So you can divert all the components that is available for you today onto your best selling products and say that these are out of stock. You can also sell some of the cars without those features for now. You could probably cut the price point, and those are very short term measures. In the medium term measures, again, people will go revisit their supply chains. They will make sure that uh, we have a stockpiling or an inventory for those critical items up to a quarter um, in our pipeline. Because a semiconductor chip supply line is not the same as a rubber or a glass windshield or a metallic chassis framework for a car. Not all supply chains are equal, and like the classic proverb of for a way want of a nail a kingdom is lost. For that one microchip that is going to complete your vehicle, the entire car is waiting in the assembly to go off. So people will go renegotiate the supplies. It also means that you need to go down your supply chain and ensure that um, everybody is in sync. Because of the multiple levels of integration with the car OEMs today, what is happening at the chip industry takes a long time to ripple and come up, bubble up. But when it bubbles up, it creates a big storm. So all the key players are now going to look at where their semiconductor chips are coming, how assured are they of the supply chains, and how do we better negotiate for our inventory. So that's going to happen in the medium term. In the long term, I see the industry itself going through an influx. There is more and more sophisticated electronics, more and more integrated systems. We call it computer on wheels. So the pivot around to electric vehicles, ADAS and autonomous vehicles, connected vehicles is going to bring more and more of the electronics and high value semiconductor chips into the cars. So it is for all the car manufacturers to also go and pivot and look at these systems in much more detail rather than just rely on the tier one suppliers to deliver the components for you and then you integrate. Because this that kind of an integration, though the modularity is there, it is not super efficient for the overall functioning. I was reading a quote that in terms of software, for the different control units, if you pull all the software lines together, it's more than 10 million lines of code. An aeroplane itself, the Boeing or the Airbus sophisticated fly-by-wire systems, has less than a million lines of code. So there is enough optimizations that can be done on the hardware software side. So it is going to be a coexistence of mechanical, electronic, software features all coexisting. So even the vehicle architecture will need to be thought about in those lines. So I would I would see, or I can even see many people go the Tesla way to play a bigger role in the semiconductor and supplies and excuse me and the car OEMs themselves don't need to manufacture it, but they can invest, they can create that ecosystem where other startups can go build the products and chips for them. That's a very worthwhile thought. So, a crisis, like I said, is also an opportunity for new beginnings. So, how do we do that, right? So, when we saw that how the manufacturing and the design process operates to create an end to end system, in each of this, so when we say India, we want to make something play a bigger role in the future of automotive, for each of these steps or parts of the specific of this puzzle here, we can go and do a lot of interesting stuff. For example, on the ideas and the IP side, we can go develop some of the low cost CPUs and microcontroller units which can be locally sourced for our automotive industry. They can even be sourced by other tier one suppliers, and it brings the overall cost function down. We can go and do a better integration of it also. And in that process, we create an end to end expertise in that domain. So, a processor unit, right from concept to the final deployment in a car and how the processing happens. If you create that ecosystem, you have all the expertise in each stage of the way. And that's how you can have a roadmap for a certain product or a system or a feature to keep building over time. And when you do these things over time, these systems to be interoperable will need a standards, and we can be a key player in the standards because we have developed these systems end to end, starting from the lowest IPs to the software complexity that we need, gets us a bigger foothold in the standards body in which the the industry or the worldwide consortium works. It's a classic play that China does. China knows today that they will face headwinds in semiconductors. They might be stopped from the participation in telecommunications. They probably see that. But what is the future um, of human systems, of cities, of industries? So they want to go start building for that future in terms of electric vehicles, the autonomous vehicles, the associated smart infrastructure. Can we do better things in telemedicine um, and vision systems, monitoring, etc.? So I think that's also a play that India has to do in terms of IPs, domain expertise, systems, and standards. That's one part of the puzzle. The other is, like I said, the foundries being the malls of the cities of the metropolis. That is where a lot of action happens today. Nobody today, you can't wake up and say, hey, we need to build a foundry in India, because the expertise to put together has to come. We need to have, when you invest in it, we're talking about a couple of $1 billion here, even for some of the mature nodes, in terms of putting all this equipment and the robotics in place, the wafer handling, etc. So when you put that kind of a capital investment, you need to see the returns maybe not in a year, 2 years, but over multiple years in the future. So how do we ensure that we have one, go service our local markets? We should also be able to go develop the silicon for other vendors across the globe. What I have probably listed is some of those feature nodes or geometries which are very stable today, which are still out in the market today, and they're highly specialized for certain functions. And all of these functions that we want to realize in these geometries can play a very significant part in our automotive ecosystem. For example, the 130 nanometer process can realize a lot of these power electronic devices for our electric vehicles, etc. The 5565 nanometer is very good in terms of its functionality and cost for Internet of Things, can go for the smart infrastructure stuff. And 28 nanometer is a good node to realize the CPUs and MCUs that can go into the automotive central processing units. Other than realizing and manufacturing silicon wafers, there is even a very big demand in the market today for very simple capacitors, resistors, filters, etc. For example, an electric vehicle car, as I read in some report, can easily have about 10,000 capacitors required. So we need to have the surface mount technology in and and there is enough volume within India to go and have it a Make in India initiative. That's two things, at least on the foundry and manufacturing side, that I can think of, which will add a lot of value for us long term. And then we talked about packaging. Packaging is also sophisticated. We are talking about like these skyscrapers on silicon, multiple chips sitting on top of each other, and they talk to them through their lifts or pillars, copper pillars. They connect from one chip to the other. That is advanced packaging, and that industry is still nascent today. So, with the expertise and an investment which is not as significant as what is required for the foundry, you can get a foothold into that packaging. And that over time, if you look at it upstream, you can see more and more of the wafer processing aspects coming into it. The key idea I'm trying to deliver here is we need to get a start, we need to get a foothold, and and consistently over time ramp up both the volumes and the technology on these different aspects. So for that, we need a very long term policy support. It cannot change when the government change or some unfortunate set of events happen. It has to be looking out for 5, 10, 20 years. We need the infrastructure. A foundry consumes tons of electricity, and it needs a specialized supply chain locally in terms of the wafers, chemicals, and the other aspects. Engineering manpower is the third. We need specialized skills to operate the foundry and the packaging and the supply chain associated with it. All three put together will help us get a foothold and over time ramp up on the Make in India initiatives. So today, if you see where the key foundries are, America used to be where all the action was. There is still sufficient foundries there. Intel and Micron between them have substantial volumes. We hear TSMC and Samsung also going to build these foundries in Arizona. In Europe, it has been just global foundries. Of course, Bosch has a facility now in Dresden, Germany. A lot of key players have been in East Asia between Korea, China, Taiwan, and Singapore. So, when do we see one in India? Um, I'm sure we will succeed in the Make in India for the electronic components. It has to be an end to end effort, right? From concepts and idea on the design phase, on the manufacturing assembly, and then in terms of building components and uh, systems. So, with that, I end this presentation and then we'll open up for your viewpoints, questions, ideas, etc. Thank you.
Hello, Narayan. Am I audible?
Harsh, yes.
Yeah. Hi. Uh, we really appreciate that. It's this couldn't have come at a better time.
Yes, yeah.
Yeah. No, I think people have been hearing a lot, reading a lot of news on this front, right? As to the chip shortage affecting the industry, but it's good to understand what that ecosystem is and why we are where we are. And I mean, I have a question. So there was, then an announcement, or not an announcement, but more like news again lately, or it's been pretty heavy in the news lately, is the fact that IESA and some global companies and stuff have, written to the government for incentives in this area for local manufacturing, right? And there is news that
Yes.
in 5 or 6 months there may be some incentive announced, some PLI sort of a scheme. So from that perspective, I have two questions. One is, let's say that something like that comes in 6 months, maybe in a year or something. There are companies who actually start wanting to work in this field, or develop foundries or fabs. One is, how skill ready do we need to be? What areas are of skill upskilling are required or are immediate? And the second is, from a sourcing perspective, right? I'm sure that even if there are foundries or fabs here, there's going to be certain materials, raw materials that would have to be sourced, or maybe a challenge from an Indian scheme of things. So how do you see that those challenges and like your thoughts on how we overcome them.
Okay. Like if you go back to the talk, we talked about design, manufacturing, assembly, and and then specifically in the manufacturing, yes, I've heard of the government giving $1 billion incentive to start
Yes.
the foundries. See, the thing is, to build a foundry, at least cost the capital expenditure is about $2 to $4 billion. Okay, the 1 billion is going to subsidize it to 25%. That is fine. Year on year, when you operate that fab, is also going to cost you $500 million in terms of all the maintenance and the electricity and all the other costs associated with it. So the key thing I would say from the government is when you put a wafer or a manufacturing facility of that sort, create enough of a local and a regional demand to at least start with. It need not be international demand. So can that demand come from the automotive or some of the industrial sectors in the country? It could even be government also, though there are a lot of security reasons there. We could always create that security measures so that the information is not leaked out. I would say that let's go create the demand in the first place. When people see a demand, they will naturally come and supply it for you. Otherwise, I would say that we are running an empty ship here. That's why, for whatever we try to kickstart, without seeing that demand, we are not able to build on those facilities. That is where we probably stuck on the foundries today.
If I may interrupt for a second.
Mm.
So I get it. Like, I mean, for any product for that matter, demand drives supply. But we know for a fact that the Indian OEM, so automotive OEMs, they are ramping up at a pretty fast pace, especially in the past 4 or 5 years. Secondly, it always does not have to be about internal consumption, right? And as you said that chips are pretty much everywhere. So I don't you believe that the demand is already there? Like, for example, a global supplier setting up a base in India, and they still, and again, what's happening with the EV field, as you see, a lot of components are situated or coming from one particular country, and that is, that sort of monopoly can wreak havoc on the industry. So from that perspective, of course, there is demand, don't you think?
Demand is there. See, the problem is the levels of integration when you see, right from a concept of a chip to a system to a module to the car finally ending up. See, that is where the value proposition changes and where it doesn't always be a regional or even a local player. So even for a car manufacturer today, many of these modules are probably Bosch, Continental, Denso, ZF, whatever. Again, they are international players. They would look for an international supply chain, right? That is then what happens when you go, like what China does for now. China makes it an incentive to whatever they call it as a make in China thing. Any given day, if there are an external competitor versus a local source, and for feature, they deliver it, the government pushes them to take the local one. It's kind of forcing the hand. We can't do
Yes.
that in the Indian ecosystem, but we can make incentives to do that. So somewhere we need to make that start at the chip level for these suppliers also to go build and deliver in India for the local market. Because again, even on the design, uh, it is not as capital intensive, but some of these software tools for the kind of analysis and verification it does is also a lot of money to invest. It's not easy to even start a chip design house, even if you have a very great product idea and a good serviceable market. So that at least I see there are some companies or some incubators who try to subsidize those costs for you to reduce the overheads and at least get you started on your feet. I see a lot of there's something called Safal here in Bangalore, Semiconductor Foundry Accelerator Labs, who can at least provide you the software tools up to a year or a year and a half, so that if you have a great idea, go build this, make money, and then you repay us or give us an equity. And when your company succeeds, we succeed. So that's, I think it's a good initiative on those kinds. And I definitely think with this pivot to electrical and ADAS systems, we are going to see more and more homegrown IP providers and companies which will deliver to the local market. I think this is a very good inflection point for the industry.
Right. I agree. I agree completely. So, going back to my original question, from an upskilling perspective and
Yes.
as well
Yeah.
as raw material perspective, what are the things like, hypothetically speaking, a lot of the regulatory and as well as incentive related things are sorted. There are companies already looking
Yeah.
to start some process within a year. Where do you start? From a sourcing and a upskilling perspective?
I think on the infrastructure side, it's all about power, power, power. Yet um, there cannot be absolutely any downtime. It's also about capacity. So very, very assured and very high power demand. But I think that we can address. I don't see an issue. What happens is when you set up a foundry, it is not just that thing is operating in isolation. You saw the different suppliers who come in, right? Very simply, the wafer. So, is there somebody who can take that ingot that you got, slice it to your requirements, and deliver it to you based on the rate of systems building? Okay, so that means one supplier, specialized supplier, there's a company called Global Wafers, would they come along and set up shop? Okay, then the specialty chemicals. There are German companies, BASF. There's a company in Japan. I think it's called um, Tokyo Electron or something. Then there is Merck. So many different companies. Would they again come and set shop? Because every time it cannot be a global shipment of these products. They need to come, sit locally, and as the demand goes, service it locally. So
Yeah.
along with the foundry comes this. It's the same thing. When you build a car, you need this whole auto ancillary guys to come along with you and be able to give the nuts and bolts for the system. So this ecosystem has to come along, of course. And then there are these specialized people now who will need to be handling those operations for either the mechanical aspects of it or the chemical engineering aspects of it. I think talent can be sought and found. It's all about training. I don't see a big overhead there. As a pretty good incentive also for people to specialize and focus in the domain. Um, and a foundry takes more overhead to set up and operate. But once you have fine tuned it on a day to day basis, operating it after the fine tuning takes no more than actually 20 people. So it's not a manpower intensive, it is a capital intensive effort, but yes, special engineering skills are required. I don't see an issue there. It's not as rocket science. Even rocket science is simple today. So I would say the right policy initiatives, Harsh. We need sustained long term policies. A $1 billion incentive doesn't cut. You're not solving the problems for them. Solve the infrastructure problems, solve some of the demand problems, create other incentives.
Yeah, I agree. I agree. I think we've already seen that in the overall EV space itself. Policies have come, they get updated, there are revisions, but
Yeah.
it doesn't seem to be a push really.
Mm,
Uh,
mm.
so yeah, good point. Okay, let's see if there's somebody in the audience who has any questions.
Yeah.
Let's switch for a second. Okay, so there's one from Atul Ahuja. Would you like to speak up, Atul?
Yeah. Tol.
Hi. Yeah, very interesting talk. So thanks for having it. Can you hear me?
Yes, Atul.
Yes.
Yeah, I think my question did get answered because my main question was that are there any IDMs who are setting up fabs in India, or is there any plant as such, a foundry as such already that exists here?
The only foundry today is there is uh, SCL in Chandigarh, but it's a government owned and operated foundry for the space and defense applications only. So it is not a high volume or a high technology foundry, but it serves India's needs in the space and defense, mainly for security reasons.
I see. And what process node is that?
I think they are like the 1 micron or a half micron geometry.
Okay. Thank you.
Yeah. I know foundries are, like I said, the malls of a metropolis. Everybody needs to have one. But given the global conditions today, it has also become a prized possession, if you will agree. So everybody wants to shape up their house before they can give it to anybody else. So Taiwan wants to very reluctantly agree to setting up foundries in the US because the US has that kind of a leverage when you're giving all these other technology to run the foundry. You can arm twist those guys and say that without this, we will cut off your supplies, right? So we need, I mean, you can, whatever it's called, arm twisting, bullying, or diplomacy. We need to get that to that kind of a leverage with the other countries and other industries also.
Right. So I see a question from Pradeep. I think most of that was already answered as far as a timeline and what challenges we see. Do you have any other questions, specific questions, Pradeep? Okay. All right, guys. I think we're pretty much getting very close to the end of the session today. Are there any more questions that you'd like to ask Narayan?
So I have a question,
Go ahead.
Narayan.
Yes, Shekhar.
There are obviously, big players that we have like Reliance and Adani.
Mm.
Should they be opening their eyes towards this field? Because some of the leverage and some of the things,
Yeah.
or, for example, Tata,
Mm.
some of them have that ability to pull it off, and they
Yes,
already have the demand. So, be it the
correct,
Geo,
correct.
be it the Tata Motors, be it Tata Communication, the demand is already there in their hand.
Mm.
So, would it take folks like those, and they own some of the raw materials as well? So, would it take some of them to pull this through?
Mm. Yeah, I think I read this about a week ago that Reliance is working with Google to um, make a custom handset, which is for the Indian conditions. That is not too OS heavy, not too many features, but can be deployed in urban, rural, very poor network infrastructure, everything. So they are working on a hardware that will service these needs. And I would think that at point in time when it becomes a realizable smartphone in hardware, the electronics assembly, the manufacturing systems would be done out of India. So I think Reliance will push for it and get it done. That gets you a foothold into now, let's say, if you want to service all the electronic components that go into that smartphones, like I was telling, the capacitors, very simple capacitors, inductors, filters. These can be like the auto ancillary parts. They will come in and start providing these local source. They need not give 100% to the local source, but at least a 60-40. And over time, when you see enough confidence, they can be the dominant suppliers. So I see where Reliance is trying to push, and I know that's just the tip of the iceberg. But I see that it will also have a trickle down effect. Adani's, I specifically don't have any data point, but they can pretty much push the envelope on the power electronics side to at least have some of the suppliers build it, design and build it out of India.
Right.
So
Yeah.
see, I always give the example of Taiwan, which even 20 or even 40 years ago was just a pure player in the motherboard assembly. You would send these boards, you would send these components over, they would solder down for it, do the the continuity checks, and then ship it back to you. But then look at where they are 40, 50 years later, right? They are at the pivot of semiconductor chip manufacturing. So we need a start somewhere. We need that spark, and then we need that continued policy support to build it up over time. And I'm sure
Right.
it'll come. I'm sure it'll come with the auto industry setting up the pace and the industrial sector following it.
Yeah.
We will see a lot of homegrown systems and chips over time.
Yeah. Thanks, Narayan.
Yeah.
I think this has been a very good discussion. Again, any parting words from your end?
Um, yeah, I make in India.
Yeah.
I strongly feel that at least in the automotive sector, um, we can do some of the homegrown features and systems that service Indian markets rather than just purely integrated from worldwide suppliers. So, be it electric vehicles, connected ADAS systems, what is it that will really help in the Indian context? And can we have that supply chain for it all local? And the same thing can be exported also. That's a
Yeah.
dream, but let's see how it comes. I'm at least very passionate about that.
Yeah. Thanks, Narayan,
Yeah.
and thanks everyone for
Thank you,
staying
folks. Yeah.
on this extended session. We'll
Yes.
also have the recording sent out to you.
Yeah.
Thank you. Bye.
Thank you. Bye.